Hello, I'm Zach Kuttner, and today I will be presenting our paper, Deadlock-Free Asynchronous Message Passing in Rust with Multiparty Session Types, which is written by me, Nobuko Yoshida, and Martin Vassor. So what is Rust? It's a systems programming language that's becoming increasingly popular both in academia and industry. The key idea is that it can provide the same performance as low-level languages, like C or C++, but with additional safety features. It offers this using a combination of static analysis and cheap abstractions. One of these abstractions is message passing to achieve safe concurrency, whereby concurrent processes communicate by sending one another messages containing data. We'll look at an example of how this can be used, along with Rust's recently added async await syntax. Here, we have a simple message passing program where we can send and receive a few messages over a channel. Ordinarily, these operations are blocking. This means that a thread can do nothing else while it waits for a message to be sent or received. However, in this case, the function is marked as async. When one of these blocking operations is performed, the result can be awaited. This improves performance since the thread can be used for other work and is notified when the send or receive has completed, so it can return to its previous execution. Unfortunately, there's still a problem which occurs with all message passing programs, and that is the potential for communication errors, such as deadlocks. To prevent these kinds of errors by construction, we turn to session types. This is a type system to prevent communication errors by coordinating message passing processes. Specifically, this project uses multi-party session types, which can type protocols with any number of participants. Session types begin with a global type, which I'm going to talk through for a simple ring protocol between three participants, A, B, and C. In this protocol, A first sends an add message containing an integer to B. Next, B chooses between sending an add and submessage to C. And finally, C sends this same message type to A. The protocol then repeats using recursion. A global type contains the interactions for all participants. We project it onto each participant to get a finite state machine containing the interactions for a single participant alone. Here, the exclamation mark denotes send, and the question mark denotes receive. For example, B's finite state machine first receives add from A, and then sends add or sub to C, as per the global type. Projection also checks the well-formedness of the global type, ensuring that it contains no communication errors. Therefore, these projected automata can safely interact with each other without any deadlocks. While there are already numerous implementations of session types in Rust, in this project we address several limitations in the current state of the art. The first is that most previous work targets only binary session types, and therefore supports protocols with only two participants. Meanwhile, the majority of real-world protocols consist of more than two participants. Secondly, although there are many Rust libraries which support message passing using async await, only the work by Chan et al. Combines this with session types. We want to achieve the performance of async await in Rust, combined with the safety guarantees that we're given by session types. Finally, the most significant limitation, which applies to all existing session type implementations in Rust, is support for asynchronous message reordering. Global types, like the one we saw previously, are synchronous by design. This is because it's straightforward for developers to reason about synchronous protocols. However, projecting a global type only provides one of the many safe possible orderings. In the projected finite state machine, for B, it first receives from A before sending to C. By swapping the order of the input and output actions for B, such that it sends before receiving as you can see on the slide, we can actually make the protocol more efficient. Let's see how this works. Originally, A sends to B before B sends to C, but with the optimized type for B, A and B can both send asynchronously in parallel, which allows the protocol to progress faster. Of course, we have to be careful when doing this. In this example, B can't have a data dependency on receiving from A, otherwise the optimization won't work, as it must have its own initial value to send. We also need to ensure that the reordering process preserves the safety properties of session types. In this work, we present two main contributions. To address the first two limitations, we introduce rumpsteak, a Rust framework for writing safe and asynchronous message passing applications. For the third limitation, we integrate rumpsteak with existing theory on asynchronous reorderings, and we present a new asynchronous subtyping algorithm, which I'll explain more about later in the presentation. But first, we'll begin by taking a look at our rumpsteak framework. Rumpsteak primarily uses what is known as the top-down approach. An application begins with a global type, like the one that we saw for the ring protocol. This is projected onto each participant to obtain a finite state machine, which can also be optimized using an asynchronous reordering, as we saw previously. We then convert each finite state machine into a Rust API which checks conformance. This API can be automatically generated, although right now I'll write it by hand so we can get an idea of how it works. Finally, developers can use this API we've just written to write safe Rust processes for each participant. The key point is that our API uses Rust's type system to ensure conformance to the protocol. We also present two additional workflows in the paper, which I won't cover in this presentation. The bottom-up approach incorporates previous work on K-multiparty compatibility, which I'll discuss a little more later in the presentation. And the hybrid approach combines the other two workflows to provide an improved developer experience. The key difference between the bottom-up and hybrid approach, compared to the top-down approach, is whereas we use code generation to generate the Rust API in the top-down approach, in the other two approaches, the developer writes the API directly, and we use serialization to convert this API back into a finite state machine. And this presents a slightly easier developer experience. But let's see how the top-down approach works in practice, taking the example of participant B from the ring protocol we saw earlier. Since the projected finite state machine produces a non-optimal ordering of interactions, we must permute B's actions to obtain the more optimal ordering we saw before. Again, we assume that B begins with its own value rather than first receiving from A. Otherwise, this reordering won't be valid, as B will initially have nothing to send to C. Next, let's see how we transform B's optimized finite state machine into a Rust representation. We begin by creating a type for each role in the protocol. This type contains the channels needed for communicating to or from other roles. For those less familiar with Rust, we use many procedural macros in our API. These are comparable to decorators in other languages. These macros perform additional code generation for repetitive boilerplate sections, allowing our API to remain straightforward and readable. Next, we declare a type for each label in the protocol, and we use an enum type as an efficient means of sending different labels over type channels. Rust's enums are similar to C++'s tagged unions or Haskell's data types. Most importantly, we represent the actions of the finite state machine using generic Rust primitives such as select and receive. Rust's enums are again useful to represent choices, as you can see on the slide, since they allow developers to pattern match on branches. Rumpsteak's API ensures that programs conform precisely to the finite state machine it's generated from. We can illustrate this with a possible implementation for role B, which runs in an infinite loop. On each iteration, the process performs an operation on the input, branches on the result of that operation, and, after performing some communication with the other participants, updates the input accordingly for the next iteration. To guarantee linearity, our primitives utilize Rust's affine typing. Each session type consumes itself when executed and returns its continuation. If, for instance, the developer forgets to execute a particular action, like we can see here, Rust's type checker will catch this error since the types no longer match up as they did before. For example, in this case, we can see that Rust's type checker spots that the select primitive has no method receive that we're trying to call. Let's now move on to our second contribution. Our final unsolved question is now to check whether an asynchronous reordering, such as the one we performed to the ring protocol, is in fact correct. We have two options here, K-multiparty compatibility, as introduced by Lange and Yoshida, and asynchronous subtyping. K-multiparty compatibility takes the proposed optimized finite state machines for all participants. It checks, up to a bound k, whether they are compatible with each other, without the use of a global type. We've integrated Rumpsteak with existing tooling for K-multiparty compatibility, which I won't cover during the presentation. Asynchronous subtyping instead takes a single projected finite state machine and its proposed optimization. It tells us whether the optimization preserves safety, regardless of the other finite state machines being used for the other participants. An asynchronous subtyping algorithm allows the subtype to reorder the input and output actions in the supertype in such a way that it remains safe to use. We saw this in the ring example, where we swapped the input and output actions for greater efficiency. A precise subtyping algorithm has previously been presented. It has been proven sound, meaning that replacing a supertype with a subtype preserves safety, and complete, meaning that we cannot extend the subtyping relation without it becoming unsound. Unfortunately, though, the problem is undecidable in general, as shown by Lange and Yoshida. Therefore, we cannot implement this relation practically. Our aim is to create a sound and decidable algorithm to approximate this relation. Although it's not possible for our algorithm to also be complete, it's still practically interesting since it can verify many optimizations from the literature. But first, let's understand why asynchronous subtyping is so difficult. For example, to verify this optimization to the ring protocol that we saw earlier, we must check that each possible execution path in the supertype has a corresponding path in the subtype. But the problem in this case is that not only is each execution path infinite due to the recursion, but there are also an infinite number of possible paths to check because of the choice. This is because each time we recurse, we can pick a different choice, causing there to be an infinite number of possibilities. In our algorithm, to address recursion, we bound the number of times these can be unrolled, and to address choice, we unwrap them only when needed, on demand. The result is that rather than checking two types, we end up with two finite prefixes, pi and pi prime. A prefix can either be empty or contain a list of send and receives, as you can see using the definition on the slide. Our aim is to reduce a pair of prefixes to show that they are subtypes. I'll show just one of our reduction rules to demonstrate how this works, but there are several more that we give in the paper. The intuition of this rule is that receives from different participants can be reordered in the subtype. If we see a receive action in the subtype that also occurs sometime later in the supertype, we can remove both, providing that there are only receives to other participants in the way, checked with the AP sequence. This is a little confusing, so let's see how it works with a couple of examples. Here, the supertype is first receiving from Q and then receiving from P. In the proposed subtype, we receive the other way around, first from P and then from Q. We can successfully apply our reduction rule to this case, and intuitively, it's safe to receive from two different participants in an arbitrary order. More formally, the receive from Q will be our AP sequence, which allows us to apply the reduction rule we saw in the previous slide. In this next example, the supertype sends M to Q and then receives L from P. The proposed subtype instead performs the send and receive in the opposite order. Intuitively, this isn't safe because, depending on the implementations for P and Q, we may never receive from P until we have sent to Q, and therefore the protocol would get stuck. More formally, to apply our reduction rule in this case, the AP sequence would have to be the send to Q. However, this violates the definition we gave for AP, since it cannot contain sends to any participant, only receives. Using our full subtyping algorithm, we show decidability by determining that our algorithm always terminates, and we also prove soundness. Let's now see how our asynchronous subtyping algorithm is implemented practically within rumpsteak. To evaluate our work, we firstly compared our framework against other session type frameworks in Rust, which do not support asynchronous message reordering. Secondly, we compared our subtyping algorithm against other algorithms for asynchronous message reordering. In our benchmarks, we looked at the runtime performance of rumpsteak compared with these other frameworks. We found that rumpsteak outperforms existing work combining Rust with session types. Moreover, optimizing protocols with asynchronous message reordering, the key feature of rumpsteak, also greatly improves performance. Interestingly, for the FFT benchmark, rumpsteak can reach a similar performance to a popular open source Rust implementation of this algorithm. In our second set of benchmarks, we compared our subtyping algorithm against previous work for binary session types only, and against K-multiparty compatibility. We found that this confirms our complexity analysis, and we can see that our algorithm is far more scalable for large protocols than these previous works. While these previous works follow an exponential increase in the time taken to verify optimizations to protocols, our work only takes a linear time. Our work also has greater expressiveness than other session type implementations in Rust, thanks to supporting an arbitrary number of participants and asynchronous message reordering. We noted that other Rust frameworks can sometimes represent the asynchronous optimizations that rumpsteak can, indicated with an amber check. But only rumpsteak can do this while preserving deadlock freedom, the key property that session types offer. In conclusion, we've presented two main contributions. First, we introduced rumpsteak, a session-based Rust framework for writing safe message passing applications. We showed how asynchronous execution and optimization is integrated into rumpsteak, and we demonstrated its improved efficiency and expressiveness compared to previous work. Secondly, we introduced a new sound and decidable asynchronous subtyping algorithm that can check optimizations to multi-party protocols. We showed how we have implemented our algorithm practically within rumpsteak, and that it offers improved scalability compared to K-multiparty compatibility. There are also many directions for future work in this project. I've listed a few examples of these on the slide in case you're interested. Thank you for listening. I'll be happy to answer any questions at the conference.